Okay, today's lecture is about existence of the Ritz-neutral probability for Black-Scholes model, and essentially this is Girsanov theorem, and so that's section 8.3.1. I'm going to do a video. I'm going to talk a bit more about it on Monday. So our goal, remember, is that for Black-Scholes we had this dB tilde t is equal to I should just by b tilde t is bt plus drift, okay, which depends on the parameter, and divided by sigma t. Okay, so that's a constant drift theta. Okay, so that's for Black-Scholes, and we want to for Black-Scholes, and what we want is change the probability so that this Brownian motion with drift just became standard Brownian motion. So this seems like magical, but it's not. I just want to give some insight about this. Okay? So remember that in probability, you always have a sample space. Okay? Those are the outcomes. And we can define random variables on omega f. Okay? Definition of random variable doesn't depend on the probability you put. The distribution does, but not the definition of a random variable. It's just a function from the outcomes to R. And let's say this random variable, so as mean mu. Now I'm talking about the distribution. So let's say under a probability P on that sample space. Okay? Now there's a couple of ways of changing the mean. Okay, so changing the drift is really about changing the mean at every time, right? So if I want to change the mean of a random variable, the cheap trick is usually just recentering. So I'm going to subtract mu. Let's say I want mean 0. I just subtract mu, and there you go, right? So it's easy to have mean 0. And so why don't we do the same thing with this? Well, it turns out that depending on the distribution of x, depending on the random variable, this might change the possible values of the new random variable. Okay, so take for example x, which is a uniform 0, 1. Obviously it has mean 1/2. And so x minus mu has mean 0, but now the values, it takes values in minus 1/2, 1/2. So the possible values have changed. The outcome of these random variables have changed. And that's not good for us, okay, because we want an equivalent probability. Remember, for Ritz-neutral probability, that means the outcomes don't change. So how can we change the mean? By not changing the possible values. Well, the way to do this is to actually change the probability on the sample space, okay? So the new probability, we're going to call it P tilde, and the only thing we're going to do is just changing the different weights that you give to every value, okay? So here's the main example. So I'm just going to do Gaussian. There's more example in the book, but what is important for us is Gaussian, normal random variable. So let's say you have a random variable which has distribution which is normal with mean mu and mean variance sigma square under probability P. Okay? Now, say that x as a PDF, okay, write f of x for that PDF. Okay, actually I don't really need that notation, but whatever. Okay? Now what you want to do, right? So if I do the expectation of any function of that random variable, it could be an indicator function, so I get the probability. By definition of the distribution of the normal, so this is just the integral of the function g evaluated at x times the density for this distribution, which is the Gaussian density right here. Okay. Now, how can I change the weights that I give to every value x in such a way that I don't change okay, the possible values. That means so what are the possible values here? So it's the whole real values, the whole real line, right? So I want to multiply that weight by a non-zero weight, okay? So I would change the possible value if what I multiply this with as value 0, okay? I don't want that. I want to multiply by something which is strictly positive in such a way that when I do the expectation, I get a normal 0 sigma square. So the mean is 0. So how do I change the weights? Well, here it's very easy. So what I'm going to do is the expectation, okay, is the following. So I'm going to add these factor. You'll see why. So they're a bit obscure. So I'm adding this factor to the expectation. Okay. So in effect, what this does is that it multiplies the density I have here by this new factor. And obviously, if you do the math, this factor is exactly such that it cancels all the factors you get from that mu when you expand the square. So what I'm going to get in the end is just the integral of g of x is the one I get for a PDF dx. All right, so this is the PDF of a normal 0 sigma square. Okay, so by adding this factor inside, so I introduce this factor inside my expectation, then I change the PDF to the one of mean 0. Okay, so what is the new probability? So P tilde is defined by, so every time, so what's the probability of an event A? Well, probability is always the expectation of an indicator function. And so it's the expectation where I introduce the factor e to the minus mu x, e to the mu squared to sigma square, the indicator function. Okay? Now, how do I know that this is a probability? Well, if I take 1 here, so the probability of everything, okay? If I take this expectation, it is actually 1, okay? So a probability, remember, so has 3 properties. The probability of the whole space is 1. So if I take the whole space, the indicator function is 1. And by the form of the MGF of a normal mu sigma square, this is 1. Okay, so this is a little exercise. So P tilde is a probability. And on top of that, this probability is equivalent to P. Okay, so what means equivalent? It means that if an event has positive probability in P tilde, it also has positive probability in P. Okay, so if an event has positive probability in P tilde, it has positive probability in P. Okay, whatever is possible for P tilde is possible for P, and vice versa. Whatever is impossible for P tilde is impossible for P. Okay, and why is that? It's because the factor you introduce here is never 0. Okay, it's an exponential. It's never 0, and it's always positive. So what you're doing essentially is you're changing the weights of the outcomes. Okay, so what is likely here might be not as likely there. Okay, this is not what this is saying. You don't preserve the probability. Okay, the probability might change, but whatever is non-zero here is non-zero there. This could be 0.00000001, and this could be 0.9999. So the probability might be very different, but if it's positive here, it's positive there. Okay? All right, so that's the most important example. So now how do you lift that to Brownian motion? Brownian motion is Gaussian, so it's very similar. So here's the theorem. I won't prove it. The proof's in the notes, but it's essentially using this fact several times. So let's read it together. So that's what we're going to use. The Girsanov theorem for Brownian motion. So if I have a Brownian motion with drift, theta, okay, that's what we want to subtract, under a probability P. I can define a new probability P tilde, where what I do, okay, is I fudge this factor inside the expectation, okay. Again, this factor, if you don't have the indicator function, it's 1, okay. So this is still a probability, okay. So you're just changing the weights, and this weight still sum to 1, okay. And under this new probability, B tilde is distributed like a standard Brownian motion, okay. So that solves the question. Let's just go for the Black-Scholes model right away. This solves the question for the existence of the RNP for Black-Scholes. So if sigma is not equal to 0, that's very important, then I can divide by sigma here. So this is my drift. Now I want a new probability for which that is equivalent and for which this drift is 0. Okay, I can subtract the drift. And so I just applied the theorem. This E tilde is just the same as putting this factor inside. Okay, and so could be any event. And so I do the normal expectation of the event, but with this extra factor in there. Okay, so it's equivalent, and also under the new probability is the standard Brownian motion. So this is really an RNP, the definition of RNP, so it satisfies that. Okay, now you may see that here I have a minus and not a plus, and here I have a B and not a B tilde. Okay, well that's because if I put in there, so this is my answer, right, of this theorem. But if I write the standard Brownian motion, the Brownian motion with drift as the Brownian motion plus the drift, and I put that here, okay, then you see that the thetas cancel. Instead of being a plus, you get a minus, okay? Why is this interesting to put it this way? Is that I can write now the factor here as a martingale. This is a martingale. This is actually a geometric Brownian motion under P. It's actually a P martingale. And that's a feature of Girsanov theorem, that this factor is always a martingale, if I write it correctly. Okay? So that's actually sometimes useful. All right. Okay. Now, let's go back to this. So let's read a little bit more about this theorem. There's a lot to unpack. Okay, so what's the idea here? Okay, is that you have a Brownian motion with drift. Okay, so that's a typical path if the drift is positive, goes up. There's a trend. Okay, so those are typical path of Brownian motion with drift, theta, positive. Now, what does this factor say? This factor should be able to make a path that is typical for Brownian motion with drift, typical for standard Brownian motion. Okay? So what it does is that for every path, I penalized where I landed. Okay? So if this is my last point of Brownian motion with drift, this is positive. And so the weight is changed by e to the minus theta, that's positive, b tilde t, so this whole thing is negative. So if b tilde is quite high, I get a huge penalty. Okay, so this weight is really small. This factor is only there so you get the whole thing is a probability. So this is a normalization factor. Okay, so really what is important is for each path, how do I weigh my path? I weigh it by exponential of minus the end point. Okay, so what happens is this probability penalizes paths that are very high. Okay, which is typical for Brownian motion. But since you penalize them, what becomes typical is something like standard Brownian motion. And this is what you have to do in the numerical project, is see that in action, okay? So what I want you to do is generate a lot of paths that are typical for Brownian motion with drift. Then you introduce that bias, okay? And then you resample the path according to that bias. So what you're doing is you're essentially sampling with respect to P tilde. And then what you're going to see, if you plot the path that you sample under the new P tilde, you're going to see a picture that looks like standard Brownian motion. All right. Now, a surprising consequence of this is that P tilde is equivalent to P, because they just differ by a factor which is strictly positive. So if E is strictly positive in P, if the event E has strictly positive probability, then it has also strictly positive probability in P tilde. So whatever is possible in P tilde is possible for P. So if I transfer this to Brownian motion with drift, I get that whatever is possible for path with Brownian motion with drift is also possible for standard Brownian motion. So that might be surprising because typical pictures look very different, okay? But what it means is that Brownian motion with drift and standard Brownian motion are actually defined on the same path. However, the weights that they give to the different paths are different, okay? And so the two distributions are different. However, they are defined on the same outcomes, if you want, okay? So it's a bit like if I have the random variable x, which is equal to 1/2, let's say on 1/2, sorry, let's say is equal to 1 with probability 1/2, and 0 with probability 1/2, and I define the random variable y, which has the same outcome, so 1 or 0, but this one is with probability, let's say, 0.99, and with probability 0.01, okay? So they share the same outcomes, however, the weights are different. It's exactly the same thing with standard Brownian motion with drift. They have the same path, the same outcome, except that the weights for the different paths are different, okay? And this is the game I played in the simulation here. So this looks like a typical path of Brownian motion with drift, and this looks like a typical path of Brownian motion without drift. However, how I generated them, this one is generated with Brownian motion without drift, and this is generated with Brownian motion with a positive drift, okay? So you see that they share essentially the same path. The only difference, so how did I generate that with a standard Brownian motion? Well, I just waited. So I applied the simulation route several times, and I just waited to see a path that is typical for Brownian motion with drift, okay? So it's atypical for standard Brownian motion, but it's still possible. So I just had to wait a long time. Same thing here. It's atypical for Brownian motion with drift, so I had to wait a long time, but I saw it eventually, okay? The probability is small, but it's not zero. Okay, so Brownian motion with drift share the same path as Brownian motion. Okay, so that allows you to change the probability by a factor here, and that's it. Okay. By the way, this factor has a name. This is called the Radon-Nikodym derivative. Okay, just so you know. All right, so this is essentially what I wanted to say. Now, two interesting questions I will discuss in the lecture. So here we change the probability by adding this factor, right, in the expectation, and that changed the drift. Can you do that? The same procedure, I put a factor and I change the volatility. In other words, if I take BT, standard Brownian motion, and I take, say, 2BT, okay? Brownian motion where the volatility is 2. Do they share the same path? And the answer is no. So the drift is very special. I cannot do Girsanov to change the volatility. Okay. Now, what if I have other models and Black-Scholes, or the drift is not constant? Can I do that? And the answer is yes. Okay, so Girsanov is really powerful to remove any drift in an etho process. All right, so this is Girsanov theorem. It's not an easy theorem, but hopefully I gave some ideas why this is true. Thank you for listening, and see you on Monday.